Working on homework?
Trying to finish furiously.
I hate to ask this, but
Yeah.
can I turn in Friday?
Friday's fine. I mean,
There's the exam today.
yeah. You have exam?
For Ian.
Uh-oh. Oh.
Sorry.
No, fine. I mean, so, okay. I will try to finish even earlier, hope.
Thank you.
Yeah, so let me write some summary before we go to the next topic. Like this.
I'm pale again. I'm pale again.
Well, think of it like this. Failure is an opportunity to learn. And I have much opportunity. Do you have a book? news for Ethan?
No.
We can go to the GTA office and use one of.
I have that Go book on a PDF file,
Oh, okay.
electronic version. Professor said one electronic version.
Yes.
So if I need, I'll.
It's clear and working. Copier.
Okay, thank you. Okay, hello.
How are you all feeling overall?
About Jan? Little stress and little worried.
How did your quals go?
Was
I was
I have TM for next
So is that who else has EM?
I'm sure I do.
You haven't looked yet?
No.
But
But
you will do it after.
Dr. Gignini was like, you will pass next time.
You will see after exam.
Did you pass classical?
Yes, I
Good.
was.
Okay, good.
I did.
Kyle said that
I
he has to
did
do the oral. exam.
Oral for
Oh, okay.
classical, right? Yes.
I give this time the
I,
last
I
time.
was
Again, I
confident
give the
on
instance.
classical and that I will pass. Also, I was confident in EM that I'm surely gonna fail, and I got.
Your confidence is right.
Yes.
Yes, sir. Did you pass all of them?
No.
Oh, okay.
Yeah, one.
That's okay.
Which time you go? Yeah. I didn't get even start.
Okay, I know you have another exam after this class, so let's start it. Some is also our intake exam. We need to speak or talk to you. All right, so now I just briefly summarize what we discussed the first part of chapter 8. So the goal is we are going to consider or discuss the identical particle. For identical particle, quantum mechanics, we know even though identical particle are identical, it is also indistinguishable. So for the indistinguishable particles, we know must possess the interchange symmetry. So that is required physically. By this recursion, we prove that this total wave function of n identical indistinguishable particles must satisfy this. If we interchange any particles, they either give us the same as before or negative sign. So these only two types of the function, or it is any states of the interchange operator. For positive, that means whatever we interchange, but there is no change. That total wave function system we call the symmetric. That means if we interchange between I and J, it will still give the same. And those systems, we already proved in the nature, is all correspond to the integer spin particles, or bosons. But so that means when you deal with the boson particles, you have to construct your total wave function must be symmetric. Another is antisymmetric. When we interchange two I and J, we get the negative sign of initial before interchange. So those for the particle or system in nature is half are integer spin, like electron, proton, which are Fermis. So what does mean? When asked to deal with the spin half, you immediately know you need to construct wave function this, not this, right? Not go to the homework, that they can do that. So second, now in general we solve the eigenvalue problem or time intermediate equation. The solution here, I use lower side here. This is a capital, right? I want to make the difference. Because here, usually this solution is asymmetric. That means does not satisfy this interchange between I and J, get either unchained or negative. Neither symmetric nor antisymmetric. So what happened? Because we need to find this solution or total wave function for the identical indistinguishable particle must satisfy either this depending on which type of particle. So we have construct. Construct wave function such that satisfy this. How to construct? We base on there's an n factorial exchange degeneracy. So that means we have the function solution here, right? Asymmetric. Then we perform the interchange with Pij. So if we have an n particle, how many perform? We have n factorial, right? So that means we have n factorial functions, those functions with the same energy, right? So then we can make a linear combination here. Then we have a linear combination. That is ideal. All this n factorial. Then construct this is symmetric. So that is the basic idea. Then we already test one case So we have, for example, here, we first consider 2, okay, identical, and in these particles. Okay. We consider first only 2 particles, but they are identical and indistinguishable. So first, construct symmetry, right? How to construct this? We so found out, I just gave you results and we already discussed it. So for the construct the symmetry, it's just simply linear combination of this, right? We have 2 particles. So 2 factorial, how much? Only 2 states, right? So the linear combination of 2 states, we already normalized, which is, I'm going to use this notation here. No any interchange. Okay, this is capital, this is lower, right? So that we put here. And plus 1, 2. And this is like so there's no interchange, so that is original. Plus here is 1, 2 interchange, right? And 2 and 1. That is last time, and we already proved it is eigenstates of Hamiltonian. It is also eigenstates of PIG. We proved that, so or we checked that. So I will not go to the details. This just gives you how to construct this symmetric. Then we also discuss how to construct antisymmetric, right? For 2 particles, identical and indistinguishable. The result, if you remember, is equal to 1 over square root 2. Okay, and the same thing, I'm going to use this. No interchange. I use here is lower, right? This is a difference. So the same 1, same 2, minus, here we have the sum, right? 1, 2, sine, same 1, same 2, and that is equal to no interchange, so that is still the same sine 1, sine 2, minus this interchange is sine 2, sine 1.
So P00 is no interchange?
No interchange, yes, that is a notation. Okay, so now, and we also double check this one is also eigenstates of the Hamiltonian and also eigenstates of the interchange. Now we go to next example, how about the 3 particles? Then we are going to extend to the general. Okay, that is 1, 3 identical and in this team so how many do we have? 3? Sorry, 6, right? 3 factorial. Here we have totally with this degeneracy, we will have n factorial states by this permutation, that linear combination now. So now, then when this is 3 particles, 3 factorial, which is 6 states, right? So now let's see. Let's first construct the symmetry. A 3 particle. Okay, how to do that? If I have a linear combination of these 6 states, that when you use the arithmetic is normalized, right? So that's 1 over square root 6. And here, let me first, and then I'm going to. So now, how many interchange? So you have first no interchange, right? Or no collision, first one. This corresponds to the P not apply. Second one is interchange between 1 and 2. P set, so that is the 1, 2, right? 1, 2 apply this state. And this 2, we have another 4, right? So now I'm going to this here. So then this between 1 and 3. That's 3. Keep the 2 here, the 1, 3 interchange. So this one is we perform 1, 3 commutation, right? That makes sense? Okay. Then we go to next. This is only performed 1 times. Now we already performed all possible at 1 time, right? Between 1, 2, or another 2, 3, right? We have another one is between 2 and 3. So keep 1 here. 2 became 3, 3 became 2. This one is correspond to P, 2, 3, right? 3 and 2 interchange. So now we have 4 states. Then we have another 2 is commune twice. Let's first commune 1, 2, and then 1, 3. So here, that is, here, this is 1, 2, right? 1, 2, and then 1, 3. So you will see here, this side 3, side 1, side 2. Is this one. This one I first commute the 1, 2, right? 1, 2 change. Then I'm going to commute the 1, 3. So that means the first one, the first, third one interchange. So then the 3, side 3 go to here. Side 2 go to here, and side 1 here. Okay, so this one corresponds to commute with 2 times, right? Commute 2 times. And the last one, I use either this one, so okay, this is a 2, right? 2 here, and this is already 1, 3, and 1, 2. 3, so 1, 2, and so that is side 2, side 3, side 1. This one is the first perform 1, 3, and then perform 1, 2. You see, the order different, they give a different result, right? So now let's see. We have 1, 2, 3, 4, 5, 6. I think they are not the same. So 2, 3, 1, 2, 1, 3. Right? So then 3, 1, 2, 1, 3, 1, 2, 1, 3, 2. Right? No any. And this one we can double check. It's the same as exact same as this one, and 3 and 2, 3, and this one also exactly equal to another one is okay. All right. So we have this, and you can check. I will leave to you because it takes some check whether it is against this Hamiltonian. It's a construct symmetric and against this it is symmetric. No change after interchange. Okay, check yourself. So that is easier. Now we go to the anti-symmetric. So for the construct symmetric, to construct anti-symmetric, we need to prove that it is after interchange, we go to the next side. So that is the way how for 3 particles, and for this construct anti-symmetric, 3 identical indistinguishable particles. Okay. How to construct, I will give you the result, and later we are going to extend, give you the general formula how to do it. So, square root, 1 over square root 6, that is a normalized factor here. And now, same thing. All the same function, but now we have some the sign here. When you keep first, first one, positive, no interchange. And the second one, there's only perform one interchange between 1 and 2, so now it's like sign. Sign 2, 1, 3, which is correspond to P1, 2. And minus this one, only perform 1, and these are all negative. Only for even performation, 0 over twice. So now we have another negative sign 1, 3, right? 1, 2, and 1, 3, yes. So sign 3, sign 2, 1. That is corresponding to you. And then minus another 2, 3. Here. So that is sign 1, sign 3, sign 2. This corresponds to between 2, 3. So you see the sum of regulation you can find here for even for odd permutation, that's the next sign, and for even now I have another 2. So this one here, this is first 1, 2, and 1, 3, right? 1, 2, and 1, 3, and it's just here 3, 1, 2. That is first perform 1, 2, and then second times 1, 3. And another plus is last one, first 1, 3, and then 1, 2. So that is 2, 3, 1. 2, 3, 1. Which is we perform 1, 3 first and 1, 2 for the second. So that equal to 1, 3, 2, 3. It's also equivalent to the performation 1, 3, and 1, 2.
Up to you.
Yes,
How are you deciding which one is negative and which one is
that
positive?
I'm going to discuss.
Okay.
Yeah, here, but you can check it is anything, and then later we are going to discuss. Okay, check. I'm going to ask you to check yourself whether it is eigenstates or common. And also check you have the permutation on this anti-symmetric function that gives us next sign. Half of mu equal to negative of original. Check yourself. Okay. Why?
Whenever you have this Pij operator, is that like the sum over all of the permutations?
All the possible, yes, like here, 0, 0, or, okay, 0, 0 doesn't know this one, right? Only for so ij is I not equal to j. Okay, let's do this one. Commute between, this 0 means no permutation. And this means any permutation between 1, 2, between 1, 3, between 2, 3. So all this one you perform that after you perform only once. So that is this case. This twice is negative, negative become plus. So I just, this is only one. If you have a pKl, that's different, right? That is, you have to put minus between plus. So here, this is only for one case. That's we give a negative. That is antisymmetric. And then you may say, why you put here negative, not here? That is the follow this. Just once you need to give a negative. That is here. Now that answer your question, right?
Yeah, that does.
Okay, good. Yes. So then later we are going to say if we have more than all the odd number of permutation, more negative, because that makes sense. If you permute 3 times, that is -1 to this 3 power, right?
Yeah.
It's still negative. Okay, good. So okay, so these 3, then we finish. Then we are usually we can derive to the end, but now we want to discuss same thing. This case, actually, we didn't say that might interact each other. So this is just identical and indistinguishable, but maybe has the interaction. So that's why I didn't separate the solution here. This is for total. Now let's consider further for this non-interacting. Okay, this is number 3, right? Okay. Now let's consider this. Non-interacting, identical, and indistinguishable particle. Now how to construct symmetric and asymmetric. For non-interacting particles, first let's consider some of the feature of this. For non-interacting, right? So now the Hamiltonian contract into the summation of each individual, right? Non-interacting. So each individual has this its kinetic energy operator plus potential operator. So then the solution. That is for this, right? So then here, then the solution, from here we have the solution. Ni, let me use epsilon. Solution, epsilon Ni, so Ni is quantum number, right? Correspond to states, I'm going to lowercase n(i). So, let's use I given states of ice particle. Values of ice. Because they are identical, so all the particles have same energy spectrum, same type of states, right? The only index is different, the particle have a different size. Okay, so now, then we come to the solution for total energy. Just simply sum over all particles. If we have n particle, right? Each particle has its energy. But here I use Ni index because maybe the first particle in this Ni equal to 1, and the second particle Ni equal to 2. So here, this is a different particle, maybe different, but all the summation for all, right? Because they are independent. So that is total energy. Then total wave function here. Okay. Total wave function, psi1, psi n, is simply the product of each individual, right? for the non-interaction. We know that if there's no interaction, the particle wave function total function is a product of each individual. Yeah. But here, that's to distinguish this one, so that for given set or configuration, we will, so here I'm going to, okay, I think I need to write down here, depend on index, n1, n2, nn. So here, if we have n particles, different particle, its occupied quantum states levels different. So that for given site, we will have energy. And correspond to that one, we also have. So here, n1, n is for a given configuration. Then once we are given a configuration, we have a given energy. Correspond to that energy, we have a correspond to the total eigenstates. But this one is asymmetric in general, because mathematically we solve the eigenvalue problem or time individual equation. We cannot get this result automatically get this symmetric or antisymmetric. In general, it's antisymmetric. So how many? We have n factorial. Okay. If we permute n1, nn, k1, for n three states, right? So as we have considered to construct the symmetric, intersymmetric, we just need n factorial in a combination. Okay, so that is the basic information. Now we are going to first construct two non-interacting identical and indistinguishable let's see, in this case, they follow the same idea, but now the only difference here, those it became a product of this. Then we're going to discuss some of the details. Okay, first one, construct the symmetric, right? Okay, construct symmetric, we follow the same thing because that's only in two particles, so only two states. One is without permutation or interchain, another is interchain between 1 and 2. So very easily, is symmetric. Okay, this function should be, if I use this normalized factor here, 1 square, so there are two states, right? Okay, two states. One is without the interchain, so that is the product here, right? The product. So this product now, okay, if I use a direct so this N1, first particle in the N1 states, right? So N1, since it's a product right here. Okay. Okay. So second one, so N2, second particle in the N2 states, position is second. That is without interchain, right? And plus one is interchain. Now here, that is, let me write down, I'm going to explain. N1, side 2, side N2, side 1. So the index here is for given states. You cannot change. You keep here. The only chain is a particle, right? So here, your interchain is psi between psi I and j. So in this case, psi 1 and 2. So here, that means if within N1 states, something like here, right, easily. So if it's N1 in 2 states, we have two. First one is a particle 1 here, particle 2 here. Second case, particle 2 here, particle 1 here. But this one are fixed, because that's fixed for the same energy, right? For given configuration n1 and 2, then now we have two possible distribution of particle. One is particle 1 in the first one, particle 2 is second. Another particle 2 in the first one, particle 1 in the second. That is second case, particle 2 in N1, particle 1 and 2. Okay, so this order, if you change this order, you will make a mistake. Okay, so here I just want you clear understand this. So then, for this case, that is I have a condition for giving. Okay, that is we have discussed for giving. So that's giving. Then we consider under the giving configuration how to construct the symmetric and asymmetric. Okay, so that's one today we construct. Now we are going to discuss. In this case, we have some more information we can discuss. Okay. So if n1 equal to n2 equal to n, what happens? That means here there's only one state, n1 equal to n2 equal to n. Then there's two particles here, right? Whatever you change or not is the same, right? So this is either particle 1, particle 2, or particle 2, or particle 1. So in this case, now you come to here. In this case, now this construct the symmetric function is equal to, let me pivot to, now here, psi n, n1 equal to n, right? Psi 1, psi n, psi 2, plus psi n, psi 2, psi n, psi 1. Are they equal? Because this the same n, right? So whatever this product equal to this product, right? Do you agree? Okay, so there is a factor 2 here, right? Let's see. There's a factor 2 here. This is not normalized, so now we are going to normalize here in this case. So now let's see. Let me first. So that is only simply the product of these two in the same space. Then after, let's normalize. After normalize, it's very easy. You normalize it, and you can see after normalization, you will have the normalized symmetric for this case if n1 equal to n2 is simply a product. And you can see if you permute interchange, this keep the same because they stay the same, right? So whatever, so that is symmetric. And normalize is very easily. You just how to normalize? Put this normalized factor here, right? And you just normalize, and you find a, which is this one. And then after normalize, this is very easy, so you can do the same. Okay, this is the first we discussed. Second, that's A, right? B, we are going to rewrite because we are going to extend to the n particle. So now we are going to rewrite psi psi1, psi2 as follows. The rewrite means that the equivalent just in different way, right? Expression, right? So here, this one is here, right? Is this one, right? So now let me first keep this one here, then we are going to write that you know they are equivalent. Okay, now I'm going to say, since this one is P00, no any permutation here is P12, right? This one just interchange, so I use this notation to apply to same. Then you can see here is summation to 2 case, so that is square root 2. If I'm going to use the summation, okay, so this sum over all possible notation. This also include the twice, right? You can some cases you also need the commute first and commute second. That is also the include all. Okay. So now this became general, but this we rewrite from the 2 particle. Then we are going to extend to the to 3 particle. Let's see, I loop here. I think I keep this symmetric and anti-symmetric together. Okay. Well, from 2, let's still keep 2. So 2 particles. This one, 2 particles for this symmetric. So now number 2, construct the just keep on it, right? Because it's a 2 particles. So this is one first construct symmetric. Now we keep on the construct antisymmetric for 2 particles. 2 non-interacting identical indistinct particles. So here, as we did before, but now this one is just a direct product of single the function, so we just do this right down here. One was going to start N1, Z1, multiply Z2, Z2, minus start N1, Z2, Z2, Z1. Okay, that is we already discussed. With this maybe interaction, but without interaction, the only difference here is just direct products of this single particle space. So this one, okay, also discuss A, E, N1 equal to N2 equal to N. Okay. One was equal to 2, right? First, N, C1, N, C2, minus N1, N, C2, N, C1 is 0, right? Because they are equal. So what that means, for asymmetric there's no such states if n1 equal to n2. So that means if I use the picture here, if this is a n1 equal to n2 equal to n, then these two states no exist. Not allow two particles in the same states. And no, that is Pauli exclusion principle. So automatically we know fermions follow that. And why? Because it's follow this anti-symmetric. So automatically the Pauli's exclusion principle proof. This is example. Now later we are going to for any other the more than two particles, right? So that is the first issue. We automatically obtain if the system follow the anti-symmetric, they automatically to prove that they for the same energy level, we cannot occupy more than one. Okay, so that one. Then we can rewrite. That is A, right? B. We are going to also rewrite this symmetry. Rewrite. That is rewrite anti-symmetry. We also want to extend it in general formula, right? How to rewrite? Okay. Same thing. So the anti-symmetric. I skip this one since I already here, right? So that is I immediately go to here. That is 1 over square root 2 without any permutation. N1, cell 1, cell N2, cell 2. Minus plus, okay, minus 1 to the first power. So that is minus, right? Okay, then I can write in general here. This summation to all the possible permutation for two particles, either no interchange, also with one interchange. So summation for all P, something like here, sum of all the possible permutation, but here we need this one. Let me see, yeah, P and P and J, so N1, N1. So you see, it's symmetric. The difference between symmetric and or the anti-symmetric is we have this factor here, and that is satisfied anti-symmetric, right? So automatically put here, and then the P, okay. Now the minus 1P is equal to minus 1 if okay. Minus, so that's minus for odd permutation and plus for even. So then you count. You just permute one times, that is odd, right? So we have a minus 1. If we have this like first 1, 3, and then 1, 2, so you perform it twice, that is even, then you get positive. So which negative, positive, this one, just you count how much permutation. In this case, we have only 2 possible. One is no permutation, that's even. Another is with 1 permutation is negative. Or more general, in this case, another general case, you don't need to count it. So we are right into this matrix. So that means another case is into the matrix. Is equal to 1 over, okay, now I'm going to also factorial. Here, 2 is equal to 2 factorial, right? And then here, square root 2 factorial. This is a 2 by 2 matrix, so now I'm going to let you know how to write the matrix. The row is states. So N1, cell 1, side N1, cell 2, and then second N2, cell 1, and N2, cell 2. So that means when you write for row, those just adding states. Just row is for ni, the chain ni from one, and the column is that. That is the way how you write. So now you can see if I write this matrix, it is automatically included like the sign, right? So you see here, the first one is N1 psi multiplied N2 psi 2. Yes, that is the first term. Positive. And then another one is this one, N1 psi 2 multiplied N2 psi 1. We have a negative sign, right? You know this how to perform the matrix, right? This is negative. So for the anti-symmetric, it's easier to remember this one. I mean, if you're familiar with this, how to perform this. Okay, so that is two particles.
Is that the determinant?
Yes. Okay, now go to 3. So 3 we have some of more discussion. Then we go to the extend to the general. So now let's consider 3 particles. Now interacting identical and in this T-verse particles. Okay, this case again we first construct the symmetric. First, use this. We know there must be n factor n is 3, right? So totally have 6 states, right? Linear combination of 6. So same as before, we not didn't consider the inductance. So that is 1, 2. Okay. Let me write down this 6th term, and then we can. I'm going to give you this one. I extend from here. So suppose this one, it works. So extend to the general. So then this is for 2 particle, 2 factor, for 3 particle, 3 factor. So here, and summation for all the permutation, Ej, psi 1, N1, psi 1, psi N2, psi 2, and psi N3, psi 3. That is general formula. And then how many we have? 6 permutations. So now the 6th one, since we are going to discuss, so I'm going to extend it. How many? 6 states, right? So first one is no permutation, right? So that is N1, psi 1, psi N2, psi 2, psi N3, psi 3. Second one is is 1, 2, right? So now let's consider 1, 2, N1 is equal to psi 2, psi N2 is psi 1, and psi N3 keep the same, no interchange. Then the third one is 1, 3, but you know, N1, psi 3, psi N2, psi 2, and psi N3, psi 1. Then next one is 2, 3. So psi N1, psi 1, psi N2, psi 3, psi N3, psi 2. Then another two is commute twice. For example, here that is okay. Twice is n1, 2, side n2, side 3, side n3, side 1. And the last one is side n1, side 3, side n2, side 2, side n3, side 1. So I have this thing, so 2, 1, 3, 3, 1, 2, 3, 2, 1, so this 1, 3, 2, 3, 2, what? Let me see here. This one is 2, 2, 1, 3, 2, yes, 2, 1, 3. 2, 1, 3 here. 3, 2, 1, 3, 2, 1, here, yes. 2, 1, it's a change, so we keep, then this, so keep this one, so that is 3, 2, 1, and this one, 3, 2, 2, 3, 1, and then the 3, 1, 2, 1. Okay. So here, that is how to extend this one to here. That is, now we are going to discuss. Discuss here. Okay. Discuss if firstly, if again there are two states are same, but third one is not same. So then you can see here there are. So let me just immediately write, I want you, I think you accept this one. Okay. So you can see N1, N2 here. N1, N2, so the 7 cosine 2, right? You will find this one the same, right? N1 equal to N2, so cosine 2, cosine 1. So this stays and this stays same, right? Therefore N3, cosine 3, N3, cosine 3 here, right? This is 3. So these two, and there's another one. This one. Yeah, whatever. So here, N1, N2 same, right? N1, N2 same. I think I have remaining 3 states. Okay, yeah, these two are same, and then let's look at these two. So this one is this one and side 1, N3 cosine 1, N3 cosine 1. This one, these two, right? These two, they're same in 3, but these two are N1 equal to N2. So these two stay the same, and these two stay same. So actually 6 states became 3 states different, right? So now we have each one has a factor 2 here, square root 3 factorial, and inside only the difference. Only difference has 3 states. These 3 states is side n, side 1, side n, side 2, and side n3 plus side 3 plus side n, side 1, side n, side 3, and side n3 side 2. And the last one is side n, side 2, side n, side 3, and side n3, side 1. So what that means, if we have a 2 energy level, if they are same, the index is same. So the states, the different, the linear combination reduce, right? Reduce because there are some of so-called kind of overparking. And then after normalize, normalization, you how to normalize. How to normalize is very easy. You just so the finally normalize the symmetric function when we have a two states are same is equal to factorial 2, 3 factorial summation p ij at n1. Now n1, n2 the same, right? So n, so 1, so n, so 2, so n3, so 3. So here, I have a numerator here. And the numerator is not, first, the 2 means the number of n I, in this case n1, right? n1. The number of n I are same among n I. So if among n I we have n I numbers, but if among them there are two, there are now it's a general number of equal states. In this case, right, n1 to n2. So we have a 2. These two are equal, so we have another factor 2. Second, then this Pij only for the permutation between n and n3, because no n1, n2. So that is for a case if we have two are equal. Then that is A, right? B. If n1 equal to n2 equal to n3 equal to n. So the same thing analysis, then we can immediately obtain this normalized, this states symmetric. It's just simply product of, okay, then if you use this one, just say this. Say one. Since here, a factor becomes 3 factorial. 3 factorial multiplied divided by 3 factorial is 1. So that is number. And then here, the permutation among different. Different and I. Here, there's no different, right? So no permutation. That is this case. Okay, so now we can extend in general C. Extend to n particles. Since from 2, 3 particles we already have some of the general formula, now we are going to review just a construct for n particle symmetric. We can easily, I give you the formula and square root now n1 factorial, n2 factorial, n factorial, and the total n factorial, and one of its values, and summation of p. All the permutation, but now this permutation again is only for different. Here, n I. Is a time number of times that have the same n. So now we have n particles, and among them there are 2 same, like n1 equal to n2, so then became a 2 here. And then n2, I will give an example. N2, so n2 is equal to n1, so that is 0. Then another is, there are 3 are same, so you have N2 or factor 3. That is the count. And same thing for P here, only permutation between different. So same here. So this is N and P and G. Same thing here for different. Permutation between different states. And this only between different states. Okay. Now, this general formula we can apply to any case. Let's see example. Let's consider example. Example, we have three particles. Okay, we have n just before, right? In this case, so n1, let's see, n1 equal to n2, and in this case, we have a capital N1 equal 2, and the capital N2 equal to 0. Capital N3 equal to 1. That is how to count, right? Because when we have three particles, right? So we have say N1, N2, N3 here. Then if N1 equal to N2, so we know the capital number N1 must be 2. Since we already count N1 equal to 2, so the N2 is 0, no NA equal to N2, and then N3 is only 1. Then you have the states very easily. So that is we obtained over there, right? Is 2 factorial, 0 factorial, 1 factorial, 3 factorial, and summation here. P and G. So N1 is N right here. So N. 2. Then this is a factorial of 2 divided by 3 factors is here, right? Is this one. So same thing. Now, that is for constructing this symmetric. Now we consider construct anti-symmetric. In this case, let me just immediately use the result which we have. We have it. Either we have 2 ways, right? I just extend 2 and 3. Either equal to 1 over factorial n factorial, right? Here 3 factorial. And then summation for all the permutation with the minus 1 to the p power. And 1, and 1. Second 2, third 2. Or we can write or is equal to 1 over square root 3 factorial and the determinant, right? N1, say 1. follow the same way when we summarize in the two particles. In three particles, we just extend to factor 3 and the matrix became 3 by 3. Okay. So now,
Dr. Yu,
yes.
do you want to pass out the midterms before the
Okay.
exam?
That's time. You know that I need, because I need to expand it a little bit because that is here. Okay, now let me jump in here. That is past too quick. I have got 5 minutes, right? Let me 1 minute finish this, and I'm going to. So in this case, you know, in any case, if n1 equal to n2, right? We know if 2 rows equal, that's be 0. So immediately you have this even 3 particles. If 2 of them is equal, then that's equal to 0. So then we go to for n. Okay. So now let's just for n particles, we have immediately just use this matrix representation. You will have this cell 1 that n is 1 over square root of n factorial, and here you just n1. Again, if n any ni equal to nj, so immediately got this equal to 0. That is Pauli exclusion principle. That is no any, for antisymmetric particles, no any one state can occupy more than one particles, right? So if one of there are 2 particles occupy one state, then there's no such state. All right, so now I just very quickly give you the ideas. Then I'm going to go to this midterm exam. Now this is we didn't consider separate spin or the special case, right? Now if we consider the particle, the system has spin. So particles is spin. So in this case, how to construct the total wave function? Now I'm going to use R1, S1 for the first particle, right? Now the n particle, Sn. This is the product of a space in the space, right? R1. You can write down in the separate and the spin part S1 is n. So in this case, if you want to construct the symmetry, you just simply 2 ways. Either you construct this spatial function, this is spin function. So spatial R1, you construct separately. If 2 antisymmetric multiplied together is symmetric, right? Or symmetric spatial function is symmetric, also multiply the spatial function spin function is symmetric. For antisymmetric, you have also, if an antisymmetric spatial function, then spin be symmetric. right? Then that gives us antisymmetry. Or spatial function symmetric, then spins be antisymmetry. Okay, I just gave you the idea, and I do not have time to discuss in details from examples. Now let's go to the midterm exam. Can you, review that? And I'm going to explain the problem so that you know about the question and how to do it.
Thanks.
We have totally 5. Okay. Can you see? Okay, I have missed. Sorry.
One more for Isura.
Okay, one more question.
Oh, I thought you
I
got
thought
two.
I thought it is two, but
Okay.
single.
Yes, I will post on this Blackboard so he can get it. If you can make him, you will not. He is
they
in
are
the EML.
us.
Okay,
Yeah.
please. I mean, he prepared his exam. All right. So we have totally 5. The first one, I want you to let me know what question. The first one is about the spherical harmonic oscillator. Go back to your notes and the chapter with this. The wave function is the radial part multiplied the angle part. The radial part we have F function, which depends on the index n and L. This summation here, K, all are even number from 0 to 4 until n minus L. Textbook didn't give the n minus L because remember we discussed this the cutoff, right? So then I give you example n equal to 3 and try to write down all the possible functions for different L. So for give n and you see how many L's you can select, right? And then determine the coefficient A, K, and L. Then you will have F, N, L, R function. Then multiply this spherical harmonic, that is your total function. So key is how to determine those coefficients. I give you a pen here. Apply this recursion formula for the n AK from A naught and from A0. Second one is a little complicated, but you go step by step. We solve this this kind of hygiene-like item. We solve 3D, right? This is 2D. The only difference is 2 dimensions, so you use the polar coordinates, and I give you the potential. I also give you the Laplacian delta square, so you can write down this Schrödinger equation, Hamiltonian Schrödinger equation, right? Then prove the Hamiltonian commute with LZ. Then you can determine this wave function for LZ is only angles phi. This is very similar as the 3D for the hygiene item. Then you are going to get, when you have this angle, then you have the only radial part. Substitute this total wave function to your Hamiltonian Schrödinger equation, you get the radial equation, which I gave you already, just prove it. You can derive it here. Then when we derive here, you are going to follow the hygiene item that find the solution. Suggest use the complement type of geometric function that you first go to the low, go to 0, and go to infinite, the two asymptotic behavior. Then you have the 2 limit case, right? All the same as you follow the hygiene item, but the only difference is 2 dimension. So the formula is slightly different. Then finally you get the solution of the R law. Then you also discuss the possible allowed energy, that is F and L. Yeah. Okay. Next one is chapter 7 about this rotation, right? We have the B matrix. Just prove if the J plus minus applied to this matrix equal to that, that's A, right? And B is lower D. That is definition I already gave you. Number 4 is 3 spins. So you already homework for the 3 spins, so similar, but then you just work on different Hamiltonian or weight, right? Number 5 is this. Number 5, I have a 2 spin half. Okay, so this system an identical of non-interacting and indistinguishable construct the total wave function. So we think about what is total wave function metric asymmetry of this 2 spin system, right? And I gave you that the first is construct spin is antisymmetric, symmetric, and special function antisymmetric, symmetric, and then you just multiply and get energy. Okay, Sorry, yeah. You have an exam. You don't need. You have exam. So how about the
I
homework?
was
If you
just
finish,
trying
yeah, you
to-
can turn.
I'm working on it.
Okay. Then after exam,
Yeah.
Yeah.
send to my mailbox Friday.
Okay.
I will go to the yeah, go to my mailbox to okay. Yeah, to get yeah.
Huh.
So I will also
Okay,
send back
should
to
I
you.
complete it?
Halfway?
Yeah, like I finished 3 questions, so I have the
You,
third
you
one.
want to turn? You have another one, right?
I
Total 5.
have to do 3.27.
Okay.
No, 7 point.
It's yeah. You can Friday. If you want to send to me, that's fine. And then you send me the last one. Then you will have
Not the last one. I did the last one, then I couldn't do the third one.
Okay.
Question 3.
Question 3.
Yeah.
And it is 27, right?
Yeah.
Yeah. Okay. Fine. And you will submit that one after the exam, right? Okay. Thank you. You have to be here, right?
Yeah.
Okay, good. All right, and let me know if you have any questions. Stop in my office. We have the whole week next week, right? So you have time to think about this and to discuss with me. Okay.
One sheet of
Is that
paper.
your notes for the exam?
One sheet of paper. We are allowed
And then
to-
again,
You
whenever
are
we
allowed
have
to one-page notes?
1 page.
One
Okay,
note,
but
yeah.
you can find the back.
Oh,
Why
yeah.
not?
Yeah.
Oh, yeah.
last semester, whenever we had the final in here, and you said, you can bring your textbooks or your
But
notes
no
and
use,
stuff.
right?
It was like, just like maybe once or twice, but you bring everything that you possibly can. It's like,
Yeah.
it's like
Because we do not know
self-soothing.
which one you needed, right? Okay. I know some of you already passed some of the qualified exam, right?
Yeah.
Congratulations. Some are not, and maybe next time.
Yeah.
I know the
get
mechanics is hard. So
I didn't get any focus in
no
second
one
attempt.
passed mechanics.
Dr. Yu,
there's
we,
maybe you passed, right? Yeah.
we noticed this pattern where it's like 1 year the like subject test is extremely hard, the next year it's slightly
Extremely
easier.
easy. So you have to go to next, yeah.
Yeah.
Since hopefully you have a 2 years chance, right?
Exactly.
Yeah, that was the first one.
Let's have some stress test.
It's just inside. So, we don't have a nice view. Yeah, back.
Wow.
Oh, I mean, this.
Good luck for us.
Everything.
I mean,
Good luck.
I was.
You will do better than I did last semester. I don't think it's possible to do much worse.
In my, I will do much worse, I guess.
No.
In
I
the
got, on the midterm last semester, I got a 32.
out of
I'm not sure, I'm not ready for this Sunday.
And then you got more,
In the
right?
end, I did a little better. I had to really buckle down, go to all of the office hours that you can. But I passed. I'm done.
All right, good luck.
thank
We
you.
still have a few minutes.
Thank you.
Go and do some like stretches, Yeah. I always feel like that helps me before an exam. I'll be stretching all this week while I'm looking at that 3.5 triple particle spin problem. That's gonna be fun.
Is tomorrow due for lab 3 report? Jen?
Tomorrow, perhaps. I feel like that would be 2 weeks, like 14 days.
Yes.
So probably. He'll probably want to talk about it, but I think he's flexible. Like, if you say, hey, you had this exam.
Yeah.